All right, now it's your official welcome time.
All right, welcome everybody. These are excellent questions. We're going to have some more time at the end to answer those questions, to talk with students and faculty to get your specific questions answered, and you better all ask them today. We've got 3 minutes for each of our participating faculty members to share one slide about something that they're excited about. In between each of these, we are going to ring the gong, at which point the next faculty member should come up and push the last faculty member off the stage and get into your spiel. Faculty members, if you could kind of aggregate over here around Rick, so you don't have to go too far to come up to the front.
Over there is okay too.
Oh, that's great, thanks. Any other logistics questions before we jump into it? Jessica.
All right, like I said, questions at the end. So you each should have a handout. If you don't, we can find you one. If you have a question, write it down. We want to make sure you have. Oh, I'm mic'd. If you have a question, write it down so that you can ask it at the end or on your tours afterward. We'll divide into tours afterward. For current MSE students, graduate, undergraduate, there's some QR codes floating around for evaluation. You get to grade your professors, so have some fun with it. And it's anonymous.
And as you can already tell, professors really like to talk. So keeping us to 3 minutes is difficult. And that's why we want you to write your questions down. If you don't get a chance to ask them at the end, you can come up to us individually. You can ask one of the students. You can ask on your tour. We'll get that question answered.
All right, our first presenter is the wonderful woman you have already been hearing from. This is Dr. Amy Mall. She's our current school director and a professor, and her tagline is "Everything is made of something." All right, Linda, you ready to start the timer?
All right, so I already started talking about this, which is nice. It's like I got it more than 3 minutes. It's kind of cool. But you already asked me, what the heck do you do with a material science and engineering degree? And I said, everything's made of something. Materials are in everything. You might want, if you're my age, you might be worried about I'm going to need a hip implant and I want it to last longer. Maybe you have a grandma or mom who had a knee or hip replaced. And it's like, we'd really like that material to last longer and to bond well to the bone and to be not corrode in your body. That's all material science. You might want to buy a new mountain bike or a new pair of skis. And you want that to be strong. And you want it to last a long time. And you want it to be lightweight, but you don't want to pay too much money. That's all about what the materials are, right? What do we make it out of? How do we do that? And you might have a supercomputer in your pocket. The amount of computing power, the amount this thing could do when I was your age would have taken up 1 floor of this building. And those improvements over time are because of the materials. And because of materials improvements and how we make those materials. And not only that, I just pulled that out of a pocket where I also have my keys. And my keys have not scratched the surface of that phone. And that's because of a material called Gorilla Glass. So how we make that was material science. And I also talked about this as well. You make choices about materials every day, right? Not just in your the bike you're going to buy. But what am I going to drink my ice water out of? What am I going to have my coffee? What kind of cup am I going to use for my coffee? Yeah, Stanley cup. What's a Stanley cup made out of? Why would I not want to make a Stanley cup out of lead? Exactly. This is an awesome materials problem, right? Like lead has some really cool properties. Except unfortunately we get lead poisoning and that's really bad for us. So we might want to use something else. This is another materials problem, right? Sometimes we choose a material and it's not the perfect material. And it causes some problems for the environment or it causes some problems for our health and we have to change that material. So that process, right, of continuing to find better materials, understand materials. And what you're going to see today is everything from how do we keep something from rusting to how do we make better batteries so they last longer, to how do we make better computer chips, to how do we make nuclear power more safe. You're going to see All of that. Okay.
All right, our next presenter is Dr. Mike Hurley. All right, are we ready to go? Nope, and we do have some extra pizza. Mike, I'm gonna take it to the back in case anyone wants it. All right, if you need to move quietly because you're super hungry, pizza will be up in the back corner. All right, Mike, are you ready?
Can we update the picture?
No.
Okay.
If you show up to a photo shoot, I'll update the picture.
Yeah, right. Okay, so if everything is made of something, then also all materials change over time as they are exposed to whatever environment they are used in. So what does that mean? For me, I'm interested in how materials change as they react with the environment. Usually that's corrosion. So metals corrode. And when you think of corrosion, if you take a piece of steel and it's sitting outside or it's exposed to water, people know that it rusts. So my research is driven by trying to understand why some materials rust and how they rust or how they corrode and react with the environment. Why is it important? Because it impacts, let's see, everything around that we encounter in our life. It can have major consequences. Up on the top left there is a, let's see, this was the South Side condo collapse about 4 or 5 years ago in Florida. It was a 12-story building. Just one of the towers in it collapsed, been up for about 40 years. The collapse took less than a minute and almost 100 people died. So let's see, the reason it failed unexpectedly is because of shortcuts with construction and maintenance. But it was a ticking time bomb because we knew that the rust inside of it that was keeping that thing up was corroding. So there was a swimming pool. It was right next to the ocean that causes corrosion of rebar. We know that. And so these are things that we can prevent as long as we understand how things are rusting. Okay, so down in the bottom left is a, let's see, a utility post. Those yellow things you see all over the place, they are actually how engineers control corrosion protection systems of underground gas pipelines. So you see these things all over the place. We apply the science of corrosion to protect our gas pipelines. And so looking into the future and kind of doing research that we're interested in, on the bottom left there is a 3D printed rocket nozzle from NASA. So they are 3D printing rocket engines now. And they need to know how those materials respond to their environment. They are very concerned with corrosion. And so that is one of the things that we look into. And up on the top right is a, let's see, that's a zoom in image of 3D printed stainless steel. You're looking to zoom in about the size of a human hair. And that is unlike any metal I have ever seen. So that's pretty cool. And so we are trying to understand that and use the techniques here to help NASA build better rockets.
All right, next up we have Dr. Claire Zhang.
Hello.
You ready?
Okay. So, anyone knows what is the battery in your cell phone? What it's made of? Lithium. Yeah. So we know the lithium-ion battery actually power most of your portable electronics or your phones, your pad, and your game console. And do you anyone knows what is lithium coming from? Mines, like around the world? Is it like mostly concentrated in US? South America, yeah. So most of the raw material for lithium is concentrated in a certain area in the world. So we have the issues that sometimes we cannot get those raw material conveniently. So my group is focused on another alternative to lithium-ion battery, which is sodium. So you can use your kitchen salt to make batteries because my group is interested store energies, which is related to electricity. So that's what we call the electrochemical energy materials. So we're trying to make materials that utilize the Earth's abundant sodium, and we can use the batteries also to power your phones, your pad, and also the electric vehicles. And that we can utilize more renewable energies like solars or wind. And in my group, we are also very interested to making materials that is tens of thousands smaller than a human hair. So that's what we call these nanomaterials because they have a lot of properties that you cannot see in the bulk materials, and they can show a very good storage behaviors used for batteries. And we are also interested to look at the materials that are not perfect because we are living in an imperfect imperfect world. So we are likely to look at the imperfections and make use of those imperfections to make materials that has new properties that actually can enhance our the quality of our living. So this is one of the work we do, like you see the images on the right is we're looking at the different imperfection of the materials and see how that they can show some unique properties for batteries and also for the extreme environment like in space. And we're also trying to look at the phenomena because the batteries are dynamic. So you charge and recharge, right? So we want to look at what is going on when you are operating a battery. So we use a different method trying to zoom in to look at the performance. Okay, thank you.
All right, and our next presenter is Dr. Brian Jaquist.
Well, hello. I am Brian Jaquist, and I am the director of the Advanced Materials Lab. And I don't know if you guys have seen those race cars that have too many bumper stickers. That's what this slide's going to end up like. So, what are you doing?
You're making me do the animations?
No, you're just, I'll do them. I'll do them.
Hey,
I got
do
them.
your animations.
Okay. So we're making materials that matter, right? That's kind of our slogan. We're making materials that's involved with everything. My specific lab is comprised of undergrad students, high school interns, not unlike yourself, research or graduate students, undergraduate students, and postdocs, research associates. And we're very collaborative. We work with a lot of different universities, a lot of different national labs, and we present and work with them to solve some of the world's problems right now. So the research focus for my group is to focus on materials for extreme environments and then nuclear energy technology. So what does that mean? Why do we care? So what it means is we're looking at different ways to push the envelope of different materials. And we use what's this material science tetrahedron, where we're looking at how do we process or what are how does the processing affect the properties or the performance or the structure of the material, and then we figure out what that is and correlate how it performs through a characterization. So you've probably seen something like this before, and this is two cooling towers for a nuclear reactor, right? And so a nuclear reactor is essentially a very expensive and very fancy way to boil water. That's all it is. So we take something like this, which is a nuclear fuel pin, and based on the nuclear reactions that occur, heat is generated. That heat's transferred to the water, and then the water goes through a steam turbine, and the steam turbine powers a generator, and that's how we get electricity from nuclear power. Now, I'm not sure if you're aware, there's something like 760 million people in the world right now that don't have access to electricity. There's 2 billion people that don't have clean water. And so that's the driving force of why we look into nuclear energy, is how do we make it more accessible? Now, one of the challenges with nuclear is the time it takes to innovate. How do we make things and understand how they're going to perform so that we can make it safe? So you've probably all seen something like this. This is a 3D printer. This is a extrusion of a plastic, and you can make these really cool, complex shapes. But did you know we could also do that for metal? So I have a couple examples here, and they're two different technologies. They're also here, and you can come take a closer look later. This is done with the laser, and then it has a wire feed, kind of like a welder. That was 3 minutes.
Here, give it to the next person. Give it to Amy.
Who?
Give it to Amy. All right. And this is why we have the gong, because they could talk all day about their favorite subjects, which we love, but we also don't have all day. So our next presenter is Dr. Rick Ubik.
Hi, everyone. Happy Groundhog Day. I'll try not to repeat myself, though. You haven't maybe already been introduced to this. Brian showed a more complicated version of the material science triangle. He called it a tetrahedron. So let me introduce you to the simplified version. Processing, structure, properties. We do all of this, and we're interested in all of this in our lab, but we're mostly interested in the structural characterization of materials. And for us, that mostly means functional ceramic materials. Now, a functional ceramic is just a ceramic material with interesting or useful electrical, magnetic, or optical properties. Our main tools are X-ray diffraction, which is a better pointer, and electron microscopy. These are tools that help us actually identify where atoms are in a material. And there's, at any given time, there's several different research threads going on in the lab. I can't talk about all of them, but one of the main ones is correlative structural modeling. A correlative model is just a mathematical way of correlating some easily obtainable parameter, like ionic sizes, to something else, like a structural parameter or a property. So for example, the graph there shows effective vacancy sizes versus T. That T parameter is just a simple function of ionic sizes, and a vacancy is just a place in a crystal where an atom should be, but isn't. Very common type of crystal defect. Now, for ionic sizes, we have numbers for pretty much more or less the whole periodic table, but what about vacancies? How big is a vacancy? You might think to yourself, well, it's zero, right? There's nothing there, it should be zero, but you'd be wrong. If we fit an equation to that curve, we can calculate exactly how big a vacancy is for any compound in that structural class. Now, that's important for things like a crystal size prediction, that is predicting how far apart atoms are in a crystal. And that's important for things like thin film depositions. We can also use the same sort of technique for all sorts of other structural effects that have important implications for properties like ionic conduction, for example. So one of the other research threads in the lab is to do with damage in graphite due to irradiation damage in graphite. So this movie down here, in fact, shows different kinds of defects moving around under the influence of an electron beam from that instrument up there. You see the two people, one of them is me. And the thing here is that we see large dimensional changes in graphite, even at low dose rates in the field. So what's needed is some mechanism that can amplify the damage that we see here. And in 2011, what's called a Buckle-Ruck-and-Tuck mechanism was proposed for graphite, for distortions in graphite. And it was proposed theoretically. And in 2019, our group found the first evidence of that defect.
All right, Amy. Rick, some people are going to lose some bets. We thought you would be one of the ones that stayed on time.
I tried.
All right, our next presenter is Dr. Lon Lee.
Thank you.
If you can breathe, this is the halfway, getting to the halfway point.
Okay, let's go. So I'm so glad I see some of my students normally are in my class and the labs. And then so normally it's like I grade them. And today I just realized, okay, they are going to grade me. So that's why like my motivations is like when I prepare my presentation, I say, okay, if my student going to challenge me, what kind of question they're going to ask me? So that's what my presentation. So probably they will ask me, Dr. Lee, can you use one sentence to describe what material science and engineering is? So if that is the question, then I will answer them. Actually, material science and engineering is to determine the processing, structure, property, and performance relationships of the various materials. And then the next, probably the student will ask me, hey, Dr. Lee, how do you like conduct the material science and engineering research, right? What kind of method you're going to use and to define or determine that relationship? So I tell you, in my labs, and we combine experiment, so which is like you do something in your labs, and we also use computer. For example, you can use some code and you can use a software, right? And to simulate the materials and you are interested in, or you have some question you want to, hey, computer, can you tell me what kind of property this material will have under certain condition, something like that. And then we also use something called artificial intelligence. Probably you heard that every day, right? And, or we can call it machine learning. And so you may ask me, what is machine learning? Machine learning means like machine learned. So just like you train your student, you train your kids, and then you have to teach them something. So what we teach, right? What we teach the machine is we teach the machine with some data generated from the labs and also the computers. And to make sure they understand, so make sure the machine understand after the machine is well trained, and you can use that machine and to tell you because they will work much, much faster than the computer and also experiment. And so they can like generate much, much more data. And then you can use those data to guide your experiment and then the computers. And so that's what we do in my labs. And then the next question I thought, okay, what would my student will ask me? And then probably they will ask, okay, I see you use a very integrated method, right? Combining experiment, computer, and the machine. And how are you going to use this integrated method? So in my labs, and we focus on the two projects. The first one is DNA nanotechnology for room temperature quantum computing. So probably some of you already heard of quantum computers. So that's what we target. But the problem for the current quantum computer is like super large, and also they have to work in a very, very extreme environment, like probably like 4 Kelvin and degree. And then so that's impossible for us to use it, right? So that's what we try to do is how can we make it more portable? Thank you.
All right, so one of the very important things to know about very smart people is they don't always like following directions. And while sometimes it's frustrating, we like that about them. So we have Dr. Ryan Pensack and Dr. Bill Knowlton here, and they're actually going to do an experiment. And I'm going to yield the computer to them, but they do still get the 3-minute rule.
Go ahead and advance.
You ready? Okay.
We hate following rules. So welcome. The Quantum DNA Research Group, we call ourselves QDNA. Our ultimate goal, and you just heard Dr. Lee talk about it, is quantum computing at room temperature. The approach, mimicking photosynthesis, a very complicated, difficult problem, and it requires many experts in the field to solve it. And so this big question that the experts need to solve, the quantum or QDNA has 5 research teams to tackle this problem. And that's approximately 40 people that span about 10 academic disciplines. Dr. Ryan Pensack, who we recruited from Princeton, and Dr. John Huff, who just received his PhD here in material science and engineering, are part of, and myself are part of Quantum DNA, and they will be doing this demo.
Thanks, Bill. Let me switch over the screen here.
Oh, stop share and then change camera. Camera's coming. I just want to switch to that camera, right?
Yeah, but we need it over here so it displays. Great. Thanks, Bill. Yeah, as Professor Knowlton mentioned, our group's research focuses on room temperature quantum materials. So to illustrate how these materials work in computers, let us first consider how current computers work. And I'll mention this is an adaptation of a really nice video by researcher Tali Gershon at IBM. So shown here is the capital letter B, and what a computer sees actually is a specific combination of zeros and ones shown here. And this is actually how your computer calculates things such as the internet, even displays videos on YouTube. And we can also depict these zeros and ones as the color blue or the color orange. So now let us consider a third state, a state where the coin is spinning. When the coin is spinning, it is sort of a combination of blue and orange. And this is called a superposition. And it's a sensitive and fragile state. It's the most basic ingredient of a quantum computer. And we want the spinning to be fast and long to enable us to approach solving new problems in a fundamentally new way. Our research group here in material science and engineering works to synthesize new coins that spin really fast and for a long time. We also build tools, unlike any other in the world, that to characterize how fast they spin and how long they spin. And finally, we predict how to make these coins spin fast and long.
All right. Peter, there we go. There's Peter. Let me get the screen back shared again, okay? So our next presenter is Dr. Peter Molnar. Let me double check the screen is sharing before we continue. I said, very smart people don't always like following directions, but we know that about them, so it's okay. All right, Peter, you are up.
Thank you. Clean energy magnets. We currently live through a transition from fossil fuel powered economy to a battery powered economy. We have lived through such transitions from burning wood to burning coal, steam engine, the Industrial Revolution. Then we started burning diesel or oil or gas, cars, individual transportation. And now we go to batteries. Through all these transitions, there have been opportunities, there have been winners, there have been losers. People got rich, people got poor. Countries became powerful, some countries lost their power, all depending on whether or not they could get direct access to the resources that were required for the new energy source. So how will America do? How will you and I do in this new transition to going to battery-powered economy? Well, through all these transitions, technology became more complex. A car in 1950 needed maybe 20 elements of the periodic table: iron, copper, silicon, oxygen, some more. You could make a car. Today, our electric vehicles have maybe 80% of the periodic table. Some of these elements, they use only a very tiny little, but without them, the cars won't drive. So where do these materials come from? Some come, as we have learned about lithium, it's also an electric vehicle, from single countries. They have monopolies. That puts America at a risk. Those countries have political leverage over us. Also, it puts us at a national security risk. Our armed forces, our military needs technology that uses those type of materials. If we don't get them, we have no strength. And then is the risk of our economy. If we don't get these little tiny materials from foreign countries, we will have no economy and our economy will collapse pretty quickly. So what do magnets have to do with all of that? Well, as you see, in wind turbines, the generators use strong permanent magnets for turning wind energy into electricity. And in our electric vehicles, strong magnets are used for the electric motors to work. Those strong permanent magnets, they have a lot of iron, but they also have such rare elements like dysprosium and neodymium, and they only come from one country. The country is China. Okay. So to secure our economy, to be independent of foreign countries, to have a military that is strong, we need to have strong magnets without rare earth elements. Thank you.
All right. So as you saw, we had Dr. Ryan Pensek up here earlier. So in addition to the faculty, we have a lot of extra smart people that get to do research even more full-time than our faculty members. And Dr. Paul Davis is one of those.
Thanks, Jess.
All right.
Is this working? Okay. Thanks, Jessica. Yeah, so I manage the Surface Science Lab along with one of my former students, Corey Ifa, who's now Dr. Corey Ifa. And in the Surface Science Lab, what we do is we use something called an atomic force microscope, or an AFM. And an AFM basically takes a cantilever, a diving board, and puts a very sharp needle at the end. And if you drag that needle over a surface, you can map out the topography. By pushing on the surface, you can also find out, is it hard or is it soft? Is it sticky? If you coat the probe with metal, you can find out, is it electrically conductive? So you can learn about electrical properties. You find out, is it magnetic? You can carry out electrochemical experiments. You can also learn about the chemical composition. And it allows you to see things that are too small to see with the naked eye. You can see at the nanoscale, which is like a millionth of a millimeter. So 10,000 times smaller than the width of a human hair. So things too small to see with the naked eye, or even with an optical microscope, we can see with an AFM. And so I get to work with a lot of students. So here's some of the former students who have been in the lab, as well as many of the people you've already heard speak today, and people across the country and around the world. We get to look at all kinds of cool stuff. Everything from batteries and electronics, next generation data storage, composites, metal alloys, learning about corrosion. You heard Dr. Hurley talk about that earlier. You heard Dr. Chung talk about batteries. We also get to look at soft, squishy stuff. So we look at DNA, proteins, cells, polymers, plastics. So the whole gamut of materials. And we learn about, for example, the battery electrodes as you charge and discharge the battery in your phone. Why does the battery no longer hold a charge? What's changing about the electrode? So we can look at that, or we can look at next generation memory storage and say, if you orient the magnet up or down, you can encode information, or by applying a voltage, you can make it conduct or not. On the corrosion front, we can look at next generation coatings for helicopter rotor bearings to make the rotors turn more smoothly. Or Dr. Mall, Amy talked earlier about hip replacements. So the titanium alloy that gets used there, can you adjust the mechanical properties of that alloy so it more closely matches that of bone so you don't wear out the socket while still maintaining that corrosion resistance? Other things that we could look at on the corrosion front, we can develop novel, lightweight, high-strength alloys for the aerospace industry. So for NASA, things like that. That's actually a collaboration we've had with somebody in Australia. There's also joining materials together. So I think Dr. Jacobs talked about this, and also Dr. Hurley, like you don't want joints, like if you've got welding or soldering, you don't want that to fail. So there are other methods of joining, but all those are susceptible to degradation. So learning how do you prevent that? On the soft materials front, all kinds of things that we can do. We look at how stem cells decide whether to turn into bone or muscle or fat or cartilage that have very different mechanical properties. The effect of cholesterol in the cell membrane and how that impacts the roughness and the mechanical properties of your eye lens, so that you can actually see.
All right. Sense some restlessness. I promise we're almost to the end of the presentations, and then it'll be time for questions. But before we get there, got some good ones up. So next up is Dr. Elton Gronyard.
Thanks everybody for coming. It's really exciting to have you here. Hopefully you're learning something and something catches your interest. My research group is called the Atomic Films Lab, and you've already heard several people have used cell phones to motivate kind of some of their research, because there's lots of cool materials that build up the cell phone and are required for these things to perform. When I was your age, these things didn't exist, right? And one of the things that's cool about these is they have really good cameras that have been put into them. When I was your age, we had to take photographs that were put onto film that had to get developed. You would send it off and wait, and you'd get a pack of films and find out if your picture came out good, or if you had a blurry photo, or maybe your thumb was in the way. So that's really cool that these things can do so much. And as over the years, we've been able to take really cool pictures, and those pictures take up space. And the memory inside of these phones has grown so that we can take more pictures, right? And we can send those pictures to our friends. We can take videos. We can post videos on TickSpace and all those other things. One of the most common uses is recording videos of cats doing really cool things. right? And those cat videos get uploaded to data centers, and they store those data, the cat videos, as bits. So Dr. Pinsick already introduced the ideas of binary information, ones and zeros. So if you look at this chart up here, you can see how much data is being produced. We're right in 2024, right? So we're several hundred or over 100 zettabytes. So that's a ton of cat videos. Companies like Micron, this is like one of their favorite charts because they make the memory that stores all those cat videos, right? And if they see that arrow going up, that's really great for business. Companies like Intel and Samsung and others, they make the processors that process all those bits, right? And like in the graphics units in your computer or the central processing unit, they have 1 trillion transistors or 10 trillion transistors. So if you look at those transistors, you can see some photographs of some transistor designs, some memory designs, and you see these little lines, colors, and these look like teeth that are coated, right? Those thin film coatings are what allows these things to operate. My group studies the thin film coatings. We study the interfaces of those coatings with the teeth or the little circles and donuts and things. All those little colors on those devices, all those are thin films. And we develop new films to make these things work and work at even smaller scales. And I'd like my students to stand up if you're in the audience.
Good job, Jacob. Way to follow directions. All right. And our final 3-minute presentation goes to Dr. Eric Jankowski.
What is up? Thanks for coming out, everybody. Thanks for your patience. All right. So what do solar panels and airplanes have in common? They need the sky. That's the best answer so far. Yeah. They share electricity. Well, yeah, so they're made of matter, which has electrons. And we can make both of these from carbon-based materials, the same sorts of molecules that we are made out of. We can make solar panels and airplanes from. In fact, I've got one of these solar panels in my pocket that we can pass around. And another thing that these two materials share is that I study them in my lab. And for both of these materials, there's so much opportunity to do cool things for humanity by engineering the structure of the molecules that make these plastic solar panels or these plastic airplane parts. A Boeing 787 is about 80% by volume carbon fiber composite. It's a plastic airplane that you can fly to Japan in today. And making these parts out of plastics requires some really careful engineering and figuring out how the molecules pack, how to pick the right chemistries so that the joints that we make between these parts are strong enough so that the wings don't fall off of the plane, because if that happens, that's really bad for business. And I don't know if you've noticed, but Boeing's having some problems with doors falling off of planes right now. They didn't use our materials for those doors. I'm just saying. But where we come in is using computers to be able to predict the structure of these materials. And so that depends upon scientists and engineers learning how to write code, how to design software so that we can predict the structure that we can use to figure out what are the right chemicals to use to make solar panels that can pay for themselves in a week, like that panel that we've got passing around, versus 15 years for the silicon solar panels that we've got today, or how to weld together plastic parts to make the components of next generation aircraft more inexpensively with a lower carbon footprint to make safer planes that you can manufacture at higher rates. And we do all of this using computers. And this image was generated with some prompts to an artificial intelligence image generator. These plagiarism machines are very useful for making an effective image for conveying the concepts that I wanted to talk about today, but it's not perfect. Like if you look at the fingers and the teeth on that person on the right, like they're a little bit creepy. And Same sorts of things happen if we don't know how to use the code that underlies our modeling efforts. And so we have responsibilities as engineers to learn how to use computers, generally speaking, to help the world.